This video discusses the sampling distribution of the mean covered in Chapter 6. We wish to make a statement about a population of interest. We might want to know the average time teenagers spend social networking in a week, or the proportion of high school students who have a smartphone. We cannot interview everyone, so we pick a sample of individuals who would represent the population. We calculate statistics from the sample and try to generalize back to the population using statistical inference. We could calculate the average time spent on social networking per week for the sample. Or we can calculate the proportion of the sample who have a cell phone. There are many ways to take a sample. The easiest is simple random sampling. If we can identify individuals in the population, then we can assign a number to each one. Then we just generate random numbers with the computer. We can randomly sample households by using a telephone directory and adding 10 to each number. This only samples from households with phones. We add the 10 to ensure we dial unlisted numbers. So we sample from our population, we collect and analyze the data, then we make an inference back to the population. As we have not sampled the entire population, as in a census, there will be some variation in our statistics that we calculate. We often see different pollsters reporting slightly different results. That is expected and is due to sampling error. Not all samples are identical. Here is the number of hours spent on Facebook for a population. The histogram gives the proportion of the population for various values of the number of hours. We have superimposed a normal distribution to the histogram. If we take a sample, we obtain the mean of the sample. We could take many samples and calculate a sample mean for each sample. The distribution of all such sample means is the sampling distribution of the mean. Here is a histogram for one sample of n equal to 50. Note that the sample has a mean of 6.21 and the original population mean is 6. Here is a histogram for a sample of 400. Note that in this case the sample mean is 6.01 and the population mean is still 6. We would expect the more observations we take in a sample, the closer the sample mean is to the population mean. The central limit theorem tells us how our sample mean behaves. The mean of the sampling distribution of x bar is the population mean mu. The standard deviation of the sample mean x bar is the population standard deviation sigma divided by the square root of the sample size. If we have a reasonable sample size, say at least 30, then the shape of the distribution of x bar is approximately normal. These statements are again, the mean of the sampling distribution of x bar is the population mean mu. The standard deviation of the sample mean x bar is the population standard deviation sigma divided by the square root of the sample size. If we have a reasonable sample size, say at least 30, then the shape of the distribution of x bar is approximately normal. We use the central limit theorem to make statements about the population using statistical inference. Statement 1 tells us that we can use the sample mean as an unbiased estimator for the population mean. Statement 2 tells us that we can use the standard error to estimate the variability of the sample mean from the population mean. And statement 3 tells us that even though the population of the data is not normal, the distribution of the sample mean will be approximately normal for sample sizes greater than 30. Hence we can assume we know the distribution of the sample mean even when we do not know the distribution of the original population. Thank you for watching. In the next video tutorial we cover the scientific method.